What's that? Oh, you can touch it, see?
What's my touch?
Go touch it. The global temperature.
What's this part of the planet?
Oh, you're gonna scroll it like that.
So fun.
Sampai ikutin mo na to. Ano yun o, kunin mo yung pera.
Got it.
Kaya nga, meron pa sa kapila, sa taas, may third floor din, ha? Second floor tayo. Second floor.
Ang show natin dapat 5 minutes before, di ba?
Dito na tayo sa
so they can grow in mass. Aha. Once they pull things in, if anything falls into a black hole, they can grow in mass. I like that. Anything else in our solar system. Because of that, the sun is able to hold the planets in orbit around it. So we have our sun right here, right where my laser pointer is. Do not be afraid of that red dot. That is just me. It is not an alien. So our sun and its gravity holds these planets in orbit. Now there's another little relationship that I want us to keep in mind as scientists is the relationship between gravity that's stretched out, that has matter and energy embedded inside of it. If there was nothing in the universe, space would be flat. But once you have something with mass, like a planet, like a star, like a black hole, you have the curving of space happening. Just like there's now someone standing on that trampoline. And if you have maybe a planet moving nearby, maybe a ray of light, you can see that it gets bent. Those paths will bend where that curving is happening. This is really how we get those orbits. So if we remove the mass, we don't have any curving of space anymore. Space goes back to being flat, and those paths go back to being straight. They are no longer bent. We no longer have those curved orbits. So when we talk about a black hole, we are talking about something that is curving space to such a degree that nothing can escape from it. It's curving space. It's almost like you're falling into a well and you can't get out of it. So the black hole that we have in front of us here is moving in front of a star field. It kind of looks like a donut. Kind of looks like a forbidden donut, if you will. Do not try to eat the donut. But this is usually what we think of as the black hole, that kind of shadowy part right there. Because light can't escape from a black hole, that is really why we call it black. And it's at this little point here, that boundary, that's the point of no escape. That is where you need to be moving faster than the speed of light itself to be able to escape a black hole. And can we move faster than light?
No.
No, light is our universal speed limit. So we can't escape. Now, all of the mass of a black hole is concentrated. It is smushed into a teeny tiny little space called a singularity, a teeny tiny little point that we can't actually see. We're not even seeing where the mass of the black hole is, we can't. So black holes, very weird. But we're peeling back the layers. Where do they even come from though?
No gravity.
So there is, so amount of gravity. So there is something that needs to happen to have what we call a gravitational collapse. Black holes can come from stars, but not just any stars. We need very, very high mass stars. So our sun is one solar mass. So that is 2,000,000,000,000,000,000,000,000,000,000,000 kg. It's a lot of zeros. That's 30 zeros. That's pretty heavy. That's a lot of kgs. But our sun is a low mass star. Even though it has all of those zeros, it's a low mass star. It can't become a black hole. We need a high mass star that can go supernova, that can explode at the end of its life. So we need a different star. We're going to see what some of our options are for a star that will go supernova. Sirius A is a hotter star than our sun. It's bluer, but not that much more massive. Not even Pollux, still not massive enough. Not even Arcturus. Nope, nope, nope. Not even Aldebaran.
They're too bigger.
They're bigger, but they're not more massive. But this beauty right here, my friends, Rigel A. This is who we want. Look at our sun. It looks like a little baby. Adorable. So cute. So Rigel A is a blue hypergiant star. It is 17 times the mass of our sun. This is a star that can go supernova. So at the end of a high mass star's life, they run out of fuel. They can no longer burn through fuel to keep themselves going, to keep themselves up, to generate any more heat. So their cores will start to collapse. They'll start to shrink under the force of their own gravity. They will shrink until they cannot shrink anymore, and then they will explode, pushing out the outer layers of that star in that supernova. So this star right here, all is well for now, but it will go in 3, 2, 1. It goes supernova. So what is left behind is a cloud of gas around a neutron star. That's what the core of that star will become after it's shrunk down until it can't shrink no more. A neutron star is a really, really densely packed object. So after a supernova, you may see something like this. This is a supernova remnant called the Crab Nebula. Really famous nebula. And the outer layers of the star you can still see here. You can see as the greens and the reds, they kind of look like coral to me. You can't see the neutron star though, way too small, but there is a spinning neutron star. But we haven't gotten to a black hole yet. We still need one more step, and that step is for the black hole, or not black hole, is for the neutron star to still be too massive to be able to hold itself up. If it still can't push back against the inward pull of gravity, if the core collapses completely, that's when we get a black hole. Dun, dun, dun. So the black hole that we saw earlier was quite easy to find because of all the stars behind it. But this black hole is a little bit harder. So our poor astronaut that we see right here, I don't think they've realized that they are getting a little too close. They can no longer go fast enough to be able to escape a black hole. They're going, they're gone. Do you think the astronaut's okay? No. What happened to them?
They died.
Before that. So before that though, our poor astronaut actually got spaghettified.
Oh.
Yeah, not as delicious as it sounds. So they would have been stretched out into a long, thin, noodly strand because of the tidal forces that are at play near a stellar mass black hole. So these are the black holes that come from these stars that go supernova. They're a little bit on the smaller side, so we end up with a difference in the amount of gravity that astronaut felt, maybe at their feet versus at their head. And so they got stretched out into a noodle. Thankfully, human beings, astronauts, haven't gotten too close to black holes, but we can see those same tidal forces when we look at stars that get too close to black holes. So stars can actually get pulled apart by those tidal forces, by that immense gravity, and form a disk of swirling material around a black hole. So you may end up with a black hole that looks a little bit more like this. It's got an accretion disk around it. That's what that kind of glowing part around it is. All that swirling material that maybe came from a star, from a gas cloud. And notice the difference in color. You can see the kind of redder outer parts that are a little bit more slow moving. And then as you spiral in closer to the center, notice that it gets bluer and bluer and brighter and brighter. That's because all of that material is getting sped up to close to the speed of light. It's giving off a ton of energy, a ton of radiation, a ton of heat as well. So this is one way that we can find black holes. Black holes, they're tricky things to do. So one way is by looking out for how they are affecting their surroundings. Another way is by looking out for X-ray radiation, looking out for these signs of heated up material, of material that's moving just a little too fast. There's a lot of really indirect ways that we can look out for black holes. Not a lot of very direct ways. So coming back to Earth though, in the Milky Way galaxy alone, there is thought that there should be around 1 billion black holes. We haven't found every single one of them, but we have found a few. The yellowish crosshairs that you're about to see, those are some black hole candidates inside of our galaxy. Now the red crosshairs though, those actually depict very, very, very large black holes. These are the true monsters. These are the supermassive black holes. These are the ones that are at the center of galaxies, of every major galaxy. And this picture that we have here, this sweet angel, this is our supermassive black hole. This is the supermassive black hole at the center of our Milky Way galaxy. This is called Sagittarius A star. Now, everything that I've shown you up to this point has been a simulation, has been a model. This is an actual image that we have of a black hole. This was taken by the Event Horizon telescope, which is not just one telescope, but many radio telescopes across the entire Earth working together to form a telescope basically as big as the entire Earth that could be precise enough, accurate enough to be able to take an image of a black hole. This is big because this is moving black holes from just models. Our show talked a little bit about the nature of space, that curving of space, but we didn't really talk too much about time and how space and time are linked. and how with the curving of space comes really an effect on time as well. We talked about a supermassive black hole at the center of every major galaxy. But the work that the Event Horizon Telescope is doing is really looking at what that connection looks like. How do these supermassive black holes affect their galaxies? Also, what happens inside of a black hole? That's hard to say because once you hit the singularity, all of our science, all of our math as we know it, breaks down. So at the singularity, is that really the limit to what we can know about our universe? But here we are. We've come back full circle. Did anybody get spaghettified? Are we okay? Nobody got turned into vermicelli? No? Okay. But yeah, thank you all so much for being a lovely audience. I'll be guiding out through that door there. Do you have any questions? Thanks so much.
Ayan. It's okay. Look at Daddy.
There's mommy, there's mommy.
Ay, ikaw naman. Then si baby. Ay, naka-live ka ba?
Ito pala yung sun. Look at the sun. Okay. Put down, Jessica. Put down. Right there. Yan. Okay. Wait a little bit. Little bit. Wait. See? I will grab the sun. Yeah. Yeah, the sun right there.
Can we go down?
Go down. And then go up. Go up. Yan. See that? You got sun already. And then okay. Down. Put down. Ngalan. Now we will grab the
Isa pa.
Ikaw na lang kaya, Joy.
Ulit na.
Picture na lang. Picture lang. Picture na lang. Picture natin lang.
Thank you.
Sayang.